So the man who inspired me to go into science was Sir Macfarlane Burnet. He was a world famous microbiologist and Australian, and I read his book and I was really wrapped in the whole idea of science and the discovery and the challenging the unknown all the time. Getting into spiders was a little bit different. It was mostly because I had a fear of them and decided I had to control it. Yeah, originally I wanted to be a nuclear physicist, and then I looked at microbiology, and then I worked over to biology, and decided that we couldn't say anything about spiders until we had names for them. And the naming process is called taxonomy. It's got nothing to do with taxidermy. Taxonomy is the naming process, and it becomes quite a challenge. As we said, that sometimes you have to go back into very old specimens that are now only in Europe. The original collections are in Europe, and we can't tell what's new unless we know what's old.
Of course.
So that they have between originally they have 8 spinnerets. Most of them now have only 6 spinnerets. They lost 2. A few of them have an extra plate that's the 2. The tarantulas go down to 4, and some of them even go down to 2 spinnerets. But the big main ones have little bumps on them, and they're very tiny holes, and the silk comes out as a liquid. And as soon as it's pulled, it turns into strands. And it's different strand strength for each group. Some spiders travel in the air, like on the helicopter, and some of them travel only on the ground, and they don't need such strong silk, but they make beautiful webs on the ground as well.
Oh, fantastic. So that's the helicopter. Let me see if you can see it. The back, it's red. And back to Robert.
Well, they believe the strongest spider that has the strongest web is one of the orb weavers. It's one in South America, I think it is, or Madagascar, I can't remember exactly, but it has a web line of at least 25 metres long. But I've seen ones in Australia of the golden orb that have been even longer out at Mount Isa. There are no trees near the road for at least 40 or 50 metres, and there's this web going out into the distance. So they're a very, very strong web. And they've actually used the web of the golden orb to make a silken dress.
Oh, wonderful.
Well, they do it rather special. The doors are silk wrapped packets of soil and so forth. And when they pull the door closed, it's waterproof. And what they do is that they use the fangs from the back of the door. So if you lift open a door, you can often see the 2 fang marks. And they lock that very tightly down. And they can be there, lock that door away from water for weeks at a time. They just prepare it, and then when they're ready, they release it and then lift it open. And so it takes a lot to do that. And some birds in Western Australia know about that, and they rip the door off, and there's the spider on the other side ready for them to eat.
Interesting.
So what spiders do is that they lay the eggs, and they lay the eggs on a lovely pad, and then they put a very beautiful cover around the whole thing, so they're protected while they go through the various stages of development. And they shed their skin once inside the egg sac, and when they shed it the second time in the egg sac, then they chew their way through it and make their way to the outside. Now when they do that, they often hang around together for a while as a group protection. And a number of spiders, like the water spiders, are also called nursery spiders because the mother makes a nursery for the babies to stay there. Others, the mother wants the spiders to go away. And some of them, even the mother, as we saw, keeps the baby inside the nest, and she does it like that. So most of them are in the air to some extent. The odd thing is that the golden orbs all put their webs in the air, except the biggest one, and she goes and buries it in the ground, and we don't understand why. It's very strange. So a few spiders actually carry the eggs with them, like the wolf spiders, and the huntsmen tend to carry their eggs a little bit. And the tarantulas and trapdoors and funnel webs, they lay their eggs under the ground in their burrow, and it's like, if you can think of a pillow held up in the burrow by the corners, and so that there's plenty of air circulating and no mold or fungus grows underneath it. So these spiders develop in there, and then they remain with the mother for a time, and she probably gets food, and they bring it down, and they feed off that food as well until they're big enough and it's wet enough for them to go looking and making another burrow for themselves. It's very difficult to be sure. We assume it's about 4 or 5 drops of venom in total, and the venom gland of the redback spider is actually in the head, whereas in the funnel webs it's in the fang zone itself. So we think they can probably bite about 6 or 7 times effectively, and then after that they run out of venom. And the odd thing is that when we see the funnel webs run out of venom, they don't behave bad anymore. They run away in the corner and hide. It's really quite fascinating. They know they've exhausted it. And a couple of drops of funnel web venom is probably about 10 or 15 drops of the size of a redback venom.
Oh, wow.
So very much bigger venom, bigger a spider puts out more.
Of course.
So
yeah.
I think I've collected probably over 2,000 or 3,000 different kinds of spiders, and I've named over 400 of them. And yeah, the favourite one at the moment is still Bob Marley, the one that lives under the sea most of the time. I mean, you know, we have a thing about science, is that one of the nastiest questions you can ask is why or how does it do it? We don't know the answer to how it does it. We don't know anything about it. So it's really a good thing in science to be able to say, I don't know. It's allowable. In fact, that's what makes the next step for you kids to come along and start studying these things and find out how they're surviving under there.
Yeah.
So the first redback bite in Australia occurred in 1849 in Adelaide, but by that stage the spider hadn't been named. And the first one was named from a specimen collected at Rockhampton in 1873. So between those times, we believe what's happened is that the spider is natural to South Australia and Western Australia, and as the ships went around taking the cargo, the spiders went with them. And this has now happened with spiders going from Australia to the southern Atlantic island of Tristan da Cunha, and more recently to Japan and to Belgium and other places. It's a very easily carried spider. So named in 1873, found first in 1849 when some poor soul was bitten in Adelaide. At home, yes, I do have a few in captivity. I usually try to give them to my students and some of my friends, because I go out into the bush like this for maybe a month at a time, and they shouldn't die. They've got to be taken good care of. We need them for study animals. They're not really just pets, but we like bringing them out to show to schools, and we go to World Science Festivals and this kind of thing. So we like to keep them alive and happy for that. And I've got a couple of big ones with me that'll become my pets for the next year or two. I don't actually study the venom itself. My students do that. But there is a spider in Japan and in China, and the species is called Macrothele raveni. It's named after me. I didn't find it. They just thought I'd do nice work, so they named it after me. And they've studied the venom of it. So guess what the name of the venom is? Raven toxin. So I've had a toxin named after me.
That's great.
It's unnamed. And the only way we can get from the level of knowledge that we have, we work on, to some extent, colour, but they're very subtle differences, and the differences between the front and back leg thickness and bushiness. And what we do with these, what we'll do with her, is that we'll, once she's home and settled and fresh and so forth, we'll grab hold of one of her legs and she'll twist it off for us. She'll actually break it off under her power, and she sets off a process at the joint called using an enzyme called DNase, which just cuts the joint. And then we've got a stick of fresh DNA, and then we can do the nucleic or mitochondrial DNA sequences and figure out where in the giant complexities of the specimens that we've got that she fits. And the nice thing is then we've got DNA and we've got an animal. What I've got to so far in the research is that I've got lots of preserved animals, but we don't have good DNA from them. And this gives us the both combinations. So my student who's doing wonderful DNA work, he can do that, and then we can use that as the base specimen to name the specimen from. And you see the baby down the back here? What's what I'm trying to figure out, because the only time I've ever seen anything that indicates how they breed is when I dug one up and it had an appendix off the burrow that had a young in it. So it's found the only bit of, it's a termite mound below, and the termite mound was soft enough at some stage.
And so that is a baby down the bottom.
Yeah, there'll be at least one in there, I think so.